Hello class. This video I would like to do a example of projectile motion. And matter of fact, this is a problem that is very similar to a problem that is assigned to you in your homework this week. So it is a cannonball that's fired from an artillery piece at 30 degrees above the horizontal with a speed of 300 meters per second. What is the range of the projectile? So for the sake of time, I already went ahead and wrote down the equations of kinematics we'll be using for the x direction and the y direction. The first thing I'd like to do is I like to pull everything I need from the problem. And in this case, the problem doesn't give you a whole lot. It gives you a speed, 300 meters per second, and it gives you a direction of 30 degrees above horizontal. Now this is a velocity. So I can go ahead and draw a Cartesian. In this Cartesian, this is x direction, this is the y direction. And so what happens here is that 30 degrees above the horizontal. So x is horizontal, y is vertical. There's the speed right there of 300 meters per second. So this is a velocity vector. A velocity vector will come in useful because this velocity vector has two components. It has the velocity in the x and another component, the velocity in the y. So the velocity in the y is this, velocity in the y. So these two are velocities in the y. You have another velocity in the y right there. So these are all of these equations are calling for velocities in the y, so it's these vertical velocities. And the x direction, these velocities here are basically this leg of this triangle, and so is this one. So how would you go ahead and figure this out now? If you remember, there's a previous video in which we covered some trigonometric functions and identities you need to solve something like this. So some projectile motions, the first thing you need to do is to figure out the x and y components of certain velocities. In this case, the cannonball fired at 300 meters per second, 30 degrees above the horizontal. So the way you're going to figure this out is this leg of this triangle here is Vx. So Vx is, when you have this angle, the way it's positioned, you use cosine, 30 degrees, times the hypotenuse, which is 300 meters per second. And I'm going to approximate this. And you can check, you can try to do this on your own and check that it is 260 meters per second. And then we can go ahead and do the y. The y is a little simpler. Vy, as far as computation goes, times 300 meters per second. Sine of 30 degrees is a half. Half of 300 is a perfect 150 meters per second. Okay, so before I did anything, I took this speed with this direction and I turned it into a velocity. Then I decomposed the velocity into its horizontal and vertical components, which we call x and y components. And the last thing that I like to do to make sense of these problems is to just draw what's going on. And so there's a cannon here, and it is firing a projectile. And this projectile will travel in a parabola. Okay. So now what we know is that we have, when this projectile the leaves the cannon, we figured out what this velocity at that point there, x, is. And velocity in the y, we also know this one. They are at that point right there. Now we want to figure out what is the range of this projectile. So just so that you remember, what is the range of that projectile? I briefly mentioned what I meant by range. And range is, so let's assume this is the height of the projectile is negligible, but the range is basically when in the x position. What is the x position when this projectile returns to the original height? So the distance between this point and this point is what we call range, which would be in this case if we adopt this point to be the 0, 0 of the coordinate axis. Then this point will be the x0 component of the axis, and this here is what we call range. So implicitly I already decided that this is going to be our 0, 0 in our coordinate system. As usual, this is the plus x direction. It's implicit. We're always going to make this choice when it comes to projectile motion. Y is plus y is on the top, and the acceleration to the gravity is down 10 meters per second squared. All that's left now is for us to pick an initial and a final position. So as I said in the previous video, super useful initial position to pick is this one. So I'm going to call this the initial point, because we just happen to have the information of Vx, Vy. If I pick the point as initial, then Vx here becomes Vx initial, and Vy becomes Vy initial, because I just chose them to be the initial position. Furthermore, this is where it marks the time equals 0 point. Which means that now we're really interested in a different point. We are very interested in something brighter. We're very interested in this point right here. So we're going to call this the final point, meaning that the x position over here is the x final, meaning that we're going to define our range in this problem as the x final. Okay? So we have x initial, Vx initial, and Vx initial. Good. And we don't have anything else. Is that right? That is correct. So we only have two quantities. And now is the time to go back and revisit our equations right here. So we have 4 equations. We have now defined the 2 quantities. So I'm going to pick here. So we have this one, Vy initial, good. We have Vx initial, great, which also gives us Vx final because it's an equality. And we also have Vx initial right there. We have V initial and the Y. We have Y initial, we chose that to be 0, so that sort of goes, so this goes away because we chose to call that 0. And there was a X initial here, which drops off anyway. Okay. And anything else we have? We also have y final, right? So y final is we chose that point already. So the final point we chose is x is what we're looking for. So it's x final what we're looking for. And 0 is the y coordinate at that point. So this is initial is 0. Good. Okay, so far so good. And let's highlight what we're looking for. We are looking for x final. This is range. So the number one question I get from students is, okay, well, what equation do I use? And it all depends on what you have. So we have 4 equations to work for. We're looking for x for the range. We have what x velocity x in the initial is. We don't know the time, so this time is basically the time it takes for the trajectory to hit this final point. Good. Now we don't have time, so we could use one of these two here to solve for time. And this is where a couple of tricks can come in really useful. You can use this one right here to find time because you have this, you have what g is, you know what g is. The only thing you have left is time, right? There's a square here, and I tend to sort of, just for preference, avoid these. It is pretty simple when you end up doing, but I want to show you how to use velocity inversion. So I will argue that we also have this in purple. I'll argue we have that. And how would this help me if I had this? Well, if you had this and you have this, you can figure out time. Once you can figure out time, you can use it back in this equation to figure out x final. So the only things we get to use is we get to use equation 1 to this one, and then use equation 2 right here. So let's go ahead and do that. First of all, remember what I said about velocity inversion. It means that if you have some velocity initial here and you follow along the entire path and you get back to, we get back to the point where it has reached the original height. So let's say this is the velocity final here, velocity y final, because we chose that point to be final. That is the same as velocity initial on the y, except it's inversed in sign. So simply by making that argument, you can say the velocity y final is minus 150 meters per second. Okay. And g is also implicit. We know that g is 10 meters per second squared. And now you have everything. So just to refresh your memory, the equation we're going to use is velocity y final minus gt plus velocity y initial you can solve for time. So let's go ahead and do that. So velocity, I'm just going to rewrite it right here. Velocity final on the y equals to minus gt plus velocity initial on the y. I will just go ahead and solve this algebraically as just to show you. I'm going to subtract both sides by velocity y initial. So this gets minus g times t equals to the velocity final in the y minus the velocity initial in the y. And now all you have to do is divide both sides by g. So t equals to the velocity final in the y minus the velocity initial in the y divided by minus g. Now this g is another point of confusion a lot. This g is just 10 meters per second squared because we chose the direction explicitly in the equation anyway. So if you look here in the equation, this minus here already chose because just to make it easy, you don't have to worry about if g is positive or negative. You just throw 10 meters per second squared in there. It's just the amount of acceleration without the direction. So these are the numbers we're going to plug in just as a reminder. So I'm just going to go ahead and say t equals to, oh, let me write this better here. T equals to, velocity final in the y is minus 150 meters per second. This is minus 150 meters per second. You divide this by minus 10 meters per second squared. If you carry this calculation out, so meters per second minus meters per second, that's meters per second, divided by meters per second squared, we get seconds, which is great, which is what we're looking for. Now, this is minus 300, and so minus 300 divided by minus 10 is 30. So this is 30 seconds. Which means that once the projectile hits this point right here, it's been in flight for 30 seconds. Note how you could have easily reasoned through this yourself. And we did this in class before. Remember that this projectile started with a vertical speed right here of 150 meters per second, right? And we know that at the highest point, the velocity y is going to be 0, which means that gravity will need enough time to chip away 150 meters per second from it, which means that it will take 15 seconds for gravity to slow down a projectile from 150 meters per second to 0 meters per second. And remember, if you draw that analogy from money, right? If you had $150 and you spend $10 every day, you should know that in 15 days your bank account hits 0. And that's a useful analogy to keep in mind. Therefore, it takes 15 seconds for this projectile to go all the way to the maximum height. And the way we talked about this on Wednesday, that the amount of time that it takes for a projectile to rise is the same time as it takes for it to fall. Hence, it's going to be another 15 seconds for it to fall, leading to 30 seconds. You could have done that on your own, or you could have used the equations we used. Either method is fine by me. But now that we have this 30 seconds, all that's left is to apply this equation. And it becomes more or less one of your early homework problems, where you have a speed, Vxi, which is 260 meters per second, and that travels for 30 seconds at that speed, and so that tells me what xf, which is what the range is. So let's go ahead. The range, xf, equals to the velocity initial in the x, which is also the final and does not change, multiplied by the timing which this thing was airborne, which is now 30 seconds. So we can go ahead and carry this calculation out. 260 meters per second multiplied by 30 seconds. This, if you carry out the calculation, is 7,800 meters. Okay? That's the range. I feel that now is a good time to talk about significant figures. I'm not super picky as far as significant figures, especially for a class like this. This is kind of an introduction to physics. You kind of just supposed to be exposed to some of the core concepts of classical physics. This is not necessarily, and the labs are also very exploratory, so I'm not a huge stickler. As long as your numbers make sense, so 7,800 meters, that's a little bit of a high number. So another way that you could have written this is 7.8 kilometers. Okay. Either number is fine. What I don't want to have is to have a 6-digit or a 7-digit number followed by meters. At that point, you either use kilometer to make it a little better, or I would go ahead and use powers of 10 Anything that makes sense, that looks reasonable to you, go ahead and use it. All right, that's all for this example. Thank you very much for listening. Again, if you have questions, just reach out and have a fantastic day, and I'll talk to you all very soon.